In order to find the support reactions on the journal bearing supporting our bent rod at point A, B, and C, while the rod is also experiencing an external load of 200 pounds acting vertically downward, whereas a couple moment of 30-pound fit is exerted along the YZ plane acting at an angle of 45 degree with respect to the Y axis, we can start by first developing our free body diagram. Now, to develop our free body diagram, first thing we have to do is to identify our reference, in this case, the origin, given as our x, y, and z axis, and then create the sketch of the pipe with all the external loads, couple moment, and support reaction acting on it, along with the dimensions, so that once we are creating our moment equation, we can identify the moment created by each one of the force. So in the question, it is mentioned that the bearings are in proper alignment and exert only the force reactions on the rod. So at point A, B, and C, we only have our support force reaction. And since they are in proper alignment, it means that there won't be a support reaction exerted along the axis of the pipe. So we only have support reaction perpendicular to the axis of pipe in all the three cases at point A, B, and C. Now, once we are developing our free body diagram, we don't have to give the cross section of the pipe since it is minimal in this case respect to the dimensions and the force that is being applied. So that's why I have represented with just a green line that is showing how the pipe is placed with respect to our axis. Now, once we have did that, let's go ahead and start applying our support reactions and external loads. So to start at point A, there is a journal bearing. The axis of the pipe is along x-axis. So we will have two support reactions going along the y-axis and z-axis given as AY and AZ, whereas the external load of 200 pound is acting vertically downward. Similarly, at point B, since the axis of the pipe is along the z-axis, the support reaction will only be present along the y-axis given as by and along the x-axis given as bx. Finally, at point C, the similar fashion, the support reaction will be along CZ going vertically upward, as well as CX along the X direction since the axis of pipe is along the Y axis. Next, we can further divide our couple moment along our Y and Z component by taking the cos 45 function and the sine 45 function by projecting it along the vertical axis. Now, once we have developed our free body diagram, we can go ahead and start writing our equilibrium equations. So for a three-dimensional system, in total, we have six equilibrium equation. Three are the force equation and three are the moment equation along the three axes. So we are going to start with the force equation first. Doing summation of forces along the x direction equals to 0. In this case, I have only bx and cx acting along the x direction. So their sum should be equals to 0. This gives us a result of bx is equals to negative cx. Next, we can write our summation of forces along the y direction equals to 0. And in this case, we only have ay and by acting along the y direction. So their sum should also be equals to 0. Finally, summation of forces along the z direction. In this case, we have an external load that is acting downward, whereas AZ and CZ is going vertically upward. So our expression will be AZ plus CZ minus 200 equals to 0. Now, once we have the force equation, let's shift towards the moment equilibrium equation, and we'll start with summation of moment acting along the x direction. Now, looking at point A, since both AY and AZ are acting on the x-axis, they won't create any moment about the x-axis. Same 200-pound force won't create any moment about the x-axis. Bx and Cx, since they are in the x direction and parallel to the x-axis, they won't be creating any moment. So the moment that will be created by will be by by, that has a moment arm of 1 feet, that is going to create our clockwise moment, as well as cz, that has a moment arm of 1 feet as well, and that is going in our counterclockwise direction. Simplifying, we get our by is equals to cz. Also, we already have a result in summation of forces along the y direction where by is present there, so we can compare this and write that result there as well. Next, let's go ahead and write summation of moment about the y-axis equals to 0. Similarly, all the loads that are acting parallel to the y-axis won't create any moment. Our external load is on the origin, so that is passing through the y-axis as well. It won't create any moment. So the moment will be created by AZ with a moment arm of 2 feet, that is going to create our clockwise moment, whereas by is going to create our counterclockwise moment with a moment arm of 1 foot. Finally, cx has a moment arm of 3 feet, and that is also creating our counterclockwise moment. Now, we do have our couple moment components along the y-axis, that is 30 cos 45, that is also going in our counterclockwise direction. Adding them all together will give us our second expression. Finally, let's go ahead and write our third expression of moment, that is summation of moment about z-axis. Now, process is the same, AZ, CZ, since they are parallel to the z-axis, they are not going to create any moment. BX and BY are passing through the z-axis, that's why they are not going to create any moment. So we only left with AY that has a moment arm of 2 feet, creating our counterclockwise moment, and CX creating our clockwise moment with a moment arm of 1. Finally, our couple moment component of 30 sine 45 is also going in the counterclockwise direction. Now that sums up all the equations that we have. Now let's go ahead and simplify them to figure out the values of support reactions. So looking at our equation 2 and equation 3, we have our variables Cx and AY that is present there, whereas BX and AZ are there. So we can do the substitution method by first starting with the AZ and represent it in terms of our CZ here. That is coming as 200 minus CZ. So let's place that in our equation 2. This thing is being multiplied by 2 plus bx1, and we already know bx is equals to negative cx, so let's replace it in terms of cx variable. Then I have cx times 3 plus 30 cos 45. That is our equation 2. We can further simplify this equation. That becomes negative 400 plus 2cz plus 2cx plus 30 cos 45 equals to 0. Now, once equation 2 is simplified, let's move to equation 3 and simplify that thing as well. In this case, ay is present, and we know ay is equals to negative cz as given in summation of forces equation along the y-axis. So I have minus cz times 2 minus cx times 1 plus 30 sine 45 equals to 0. Now, after this substitution, we have these two equations that have just two variables. So we can go ahead and simplify by adding them together and solve for our value of these Cx and Cz. So once we add them together, Cz will cancel out and we're only left with one variable of Cx here. Simplifying, we get the value of Cx as 358 pounds. Now, once we have the value of Cx from our very first equation of summation of forces along the x direction, we know Cx is equals to negative of the Bx. So our Bx value will be minus 358 pounds. Once we have that, now we can plug the value of Cx in equation 3 and solve for our Cz. Simplifying, we get our value of Cz as negative 168 pounds. Now, once we have the value of CZ from our summation of forces along the y direction, we know that AY is equals to negative CZ and BY is equals to CZ. So pretty much the other two components of the support reactions can be calculated by plugging in this expression, and we get our value of By as negative 168 pound and Ay as 168 pound. Finally, Az is left. Let's plug that thing in our 200 minus Cz. That give us the value of Az as 368 pounds.